to Math 10a. This is an introductory video for derivative tests for local extrema. So I want to start off by recalling what we know from previous lessons, which is that critical points of your function are candidates for its local extrema, its local maxima and minima. And a good question would be, how do we classify them as local maxima, minima, or neither? So I want to start off by just giving a sort of visual example. So I've drawn here a function in blue, and I have picked out the critical points, 4 of them, in red here. And it's pretty easy to see that the first and last ones are local maxima, the third one is a local minimum, and the second one here is actually neither. One way we can see that is by seeing that, for example, to the left of this first critical point, the derivative is positive, which means that the function is increasing up to the critical point. To the right-hand side of the critical point, the first derivative is negative, which means that the function is decreasing out of the critical point. So in a small region around this critical point, the values of the function are going to be smaller than at that critical point itself, which means that this point is a local maximum. The same is true for this fourth critical point, even though it's a critical point where the first derivative is undefined. In that case, it actually doesn't really matter which kind of critical point you have. On the other hand, for the case of a local minimum, such as the third point, we see that on the left-hand side of the critical point, the first derivative is negative, which means that the function decreases into the critical point, and then to the right-hand side of it, the first derivative is positive, so the function is increasing out of the critical point. So that means that the function is a local minimum. The only case that remains is this second critical point here, and here we see that to the left of the critical point, the derivative is negative, so the function is decreasing into the critical point. But then on the right-hand side, the function's derivative is still negative, so the function just keeps decreasing after the critical point. So this one is actually neither a maximum nor a minimum. And so the investigation we just did is summed up in the first derivative test. If you want to see all the details, you can pause the video here and take a look. But the short version of what's going on is we've got 3 cases. If the derivative is positive to the left of your critical point and negative to the right of it, then that means that your function has a local maximum at this critical point. And this is the case, for example, at this left-hand and right-hand critical point that we looked at in our diagram. The second case is that the first derivative is negative to the left of your critical point and positive to the right of it, which is the case where we get a local minimum. So that's this example here of this local minimum on the graph. We saw that the first derivative was negative to the left, so the function decreased into the critical point, and then positive on the right, so the function increased out of the critical point. And the third case is this. If the first derivative has the same sign to the left and right of the critical point, then that means the critical point is actually not very interesting. It's neither a local maximum nor a local minimum. And that's this example here in the diagram. So we saw that the first derivative was negative on both sides, which meant the function kind of just flattens out for a bit, but still just passes through the point, and you don't get a maximum or a minimum. Now, a good problem-solving strategy for applying the first derivative test is this. First off, you find your critical points, and then you subdivide the domain of your function along the critical points. So in the diagram above, the subdivisions would be this one here, 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 and here. On each subinterval then, you find the sign of the derivative by picking some test point x0 in the subinterval, and then just computing the derivative at x0. And the reason this works is because we already found all the critical points, which are all the places where the function derivative could change sign. So actually picking any test point will do. And then now that you know the sign of f prime on each of these different subintervals, you can just classify the critical points using these criteria here of the first derivative test. So that's the first derivative test, and now let's check out what's going to be called the second derivative test. But first we need to talk about the concavity of a function. And what this means is if the first derivative of the function is increasing over an interval, then we say f is concave up. On the other hand, if the derivative is decreasing over the interval, then we say it's concave down. And the idea here is this is really easy to characterize using the second derivative. In particular, this is true because the second derivative is just the derivative of the derivative. In other words, it's the rate of change of f prime. So saying that f is concave up on your interval is the same by definition as saying that f prime is increasing on your interval, which is the same then as saying that the second derivative, which is the rate of change of f prime, is positive. Similarly, if f is concave down, by definition that means that the derivative is decreasing on I, which means that f double prime, the derivative, the rate of change of the derivative, is negative on your interval. And this leads to the second derivative test, which is super cool. And the second derivative test says that if x equals c is a critical point of f, in particular it needs to be a critical point of the form f prime of c equals 0. So the tangent line to the graph is horizontal. You don't have like a sharp corner or anything. And also, you need to be able to compute f double prime at c essentially. Then there are three cases. If your second derivative is positive, then you get a local minimum. If your second derivative is negative, you get a local maximum. And unfortunately, in the third case, if your second derivative is 0, this test won't actually tell you anything. It's inconclusive. So the picture here is that, so for example, in the case where f double prime is positive, concave up functions kind of look like a cup. And so if you've got a cup and the tangent line at some point is horizontal, it's like you're at the bottom of the cup, and that's definitely a local minimum. On the other hand, if you've got a function which is concave down, it kind of looks like a frown, and the horizontal tangent line occurs at the top of the frown, so this point here is your local maximum. Now the idea of the second derivative test is this. Suppose that f has a local maximum at c, and the derivative of f at c is 0. In other words, you've got a horizontal tangent line there. Then what that's saying is that f prime is decreasing from positive to negative at c. So I can actually go back to the diagram from before, and we'll look at this left-hand critical point. We saw that to the left of our critical point, the derivative was positive. At the critical point, the derivative is 0, and to the right of the critical point, the derivative is negative, which means that as we move from left to right through the critical point, the derivative is decreasing from positive to negative. What that means in terms of the second derivative is that the second derivative at the critical point, which is, in other words, the rate of change of the first derivative, is negative. The derivative is decreasing. So that's the idea of the second derivative test. And the problem-solving strategy that I like to use here is as follows. First, you find the critical points of f, and importantly, you have to verify that they're all of this form f prime equals 0. Because if they aren't, then unfortunately you won't be able to use the second derivative test. So verifying that they are of the form f prime equals 0 is actually very important here. And then the second step of the strategy is actually a little bit easier, I think. So you just compute the second derivative at each critical point, and then based on that information, you just classify the critical points using these three criteria, and you really hope to avoid the third case where the test won't tell you anything. So maybe you're asking, well, why do we have two different derivative tests to classify the local extrema? The reason for it is this. There's really some trade-offs. The first derivative test only involves the first derivative, so in that sense maybe it's a little bit simpler, and it'll always work based on, you just figure out the sign of the derivative on each of the subintervals. It's pretty fail-safe. On the other hand, the second derivative test is really kind of slick, so all you have to do is compute the second derivative at your critical points. That's kind of handy. But as a trade-off, you have to have your critical points of the form where the tangent line is horizontal, and also it's possible that the test might still fail if the second derivative is 0. So the second derivative test can be a little bit slicker, but unfortunately it can also fail in some cases. So my advice to you is this. If you have to find or classify the critical points of a function as a local minima or maxima, and you're already figuring out whether the function is increasing or decreasing on each part of its domain, you might as well just use the first derivative test. On the other hand, if the second derivative of f looks pretty easy to compute, maybe the second derivative test will be easier to apply. So that's all I have to say about this. Thank you for listening.